Yes, indeed. So I took this assignment as an opportunity to discuss the kind of technology that have been used in the past on the ocean side. And so obviously there's a huge amount of work that I'm going to cover. Well, it's a technology that I did not participate to, some of it I did participate to, and I will focus on the one that I did participate to, with the bias here. So it's on the ocean side. This slide you don't need any introduction to, but it's just to highlight that what basically RINGS, I believe, wants to focus on is the geometry, the characterization of the water masses, maybe the temporal variability, and the impact on the ice shelves. That's kind of the external seaward ring, which for me is the primary ring as well. So there's been a huge amount of technologies that have been deployed in the past. They go from the typical ship-based observations. They move down to high payload, autonomous observations in front of and underneath the ice shelves. It can also be deployed, like the ice fin, through a drill hole through the ice. We have phase-sensitive radars. Stations can be deployed on the ice. We have now floats that can be used as profilers in front of the ice. We have an example, gliders in front of the ice shelf, and now underneath the ice shelf. I'll cover all that a little bit more. We have seals that can be equipped, so that's for the available proven technology that could be used readily. And then on the development side, we've heard talk about deploying floats from airplanes, and that can be done, but at this stage it's actually you have to open a large latch in the back and throw a big box, and most planes can't afford that kind of thing. So the Alamo float that was used actually was designed to go through a sono buoy tube. So if you have a tube carved through the hull of the airplane, you can actually launch the float through that. Just have to go through a certification process. And then maybe if you don't want to avoid drift, because you're going to deploy it just in front of the ice shelf between the sea ice and between the sea ice and the ice, you may want to park on the seabed, so there's also some design that needs to be tested. You might want to do that and do some testing with gliders in the future, same kind of thing. And also you may want to, instead of having to land on the ice to deploy very sensitive radars or GPS, you may want to just javelin deploy them, which has been done in the past. And another thing that I won't have time to talk about, but that's coming up, is the large surface vehicle. So it's an autonomous surface vehicle, which you can think of as a secondary ship, which has all the capabilities of a small ship. So it's multi-beam, ADCPs, current profiling, temperature salinity profiling. But because it's unmanned, it can go very close to the ice and do surveys very close to the ice, look at the geometry repeatedly over time. Okay, so we have some kind of classification. We have the old large payload limited observation window. So ship, autonomous vehicle, ice fin, they can basically give you an amazing view of the system over a short period of time, and then they have to be retrieved. High logistics, that's fantastic for process studies, and they can give you this kind of thing. So 2009 we had AutoSub in the Panamanian Glacier, and it gives us a beautiful view of both the geometry of the seabed and the ice, but the temperature, salinity, and current did that back in 2014. It can also map, the base of the ice, map channels and terraces. So it's a fantastic tool. And then we have a limited payload, so typically more just temperature, salinity, but they cover a longer observational window. So if you want to look at something like a seasonal cycle, maybe a bit more, you have to go to those. So these are the gliders, the floats, the seals. Just to give you a preview of what has been done in the past, so historical observation is mostly this kind of observation, so it's ship-based floats and seals. You have these diagrams, so each column is a season, and each row the top row is actually historical all observations from CTD, so it's ship-based CTD, since from 1950 to present, probably missing a few stations, but not much. Then if you add the Argo data set, you can see that the coverage gets better all year round, but it doesn't cover the shelf seas very well, because by definition the people have been a bit they've been very reluctant to lose their floats. And then only recently the seals have been also adding a huge amount of data on the continental shelf seas, and you can see that it adds not only data on the shelf seas, but it also covers a large amount of the seasonal variability. So that's what we had, that's what we already had. We could continue doing that as part of RINGS. I would think this could be a good thing. But maybe as part of RINGS in the future would be to integrate these other sensors. So it's air deployed floats, air deployed APRS, GPS, which need to be developed again. And there's something else here. Another thing that could be part of the future is what was developed by the group of us when I was in the US, the Christensen on the glaciology side, myself for the ice-ocean interaction physics, the Craig Lee's group for the sea glider technology, James Girton for the EMFX float technology, and was all supported by Copri for the deployment. And basically the idea here is to use these long-term process study technologies to look at what's going on under the ice and under the floating ice. So typically to do that you either have to use a high payload or you have to drill through the ice. So you have to use an AUV or drill through the ice. And so here the idea was to basically have sound sources and use acoustic positioning to know, to tell the asset where it was in the water column and horizontally. So the sea gliders are buoyancy driven engines, move up and down their wings, so they can actually fly and decide where they go. The floats, they just go up and down the water column, and then they drift with the current at whatever depth you park them. So here there's a new trick that we developed, which is we were going to have a mission in strict phases where it parks at say 100 meters from the seabed, and we know, of course we do know, that the flow is going to come in for a certain amount of time. After a certain amount of time we say, okay, now you're going to drift, but closer to the ice base. And I'm going to show you some results of that. So we deployed 3 sea gliders and 4 floats in front of the Dodson ice shelf in January, February 2018. And here you have all of the observations that were made for all of the floats. So that's the Dodson ice shelf, that's the Crosson ice shelf. And you can see that it actually was extremely successful. The 3 yellow things are the beacons. So huge amount of data covering a full year. It's actually 14 months of observations. There's a lot of interesting stories. I'm going to go very, very fast over those stories. Those gliders, you know, they go up and down, and then they hover during the winter, and then they go up and down the cavity. The floats, they actually have to follow the flow, and they can give you the time scale it takes for the flow to go in and out of the cavity. They can find pathways between cavities that you may not think exist. They can provide you amazing constraints, both of them, about the geometry beneath the floating ice for your gravity inversion, for example. And they can provide you with water properties. We'll just skip that. They can provide you with seasonal values. So this is temperature varying in time over a full season. And if you compare that to, that's heat integrated over the entire water column, and that's the entire decadal observation that we had in the past. And this is what you see over one season. So if you just imagine that happens services, and that's what you should observe. And I'm just running out of time, so I'm going to thank you very much. And this is the dream scenario in the future where we have everything going up and down. Thank you.
Thank you very much, Pierre. I'm personally very pleased to see finally oceanographic applications here. So this concludes